Alright, in this video we're going to cover the second part of Lab 7, which talks about the geometric distribution. So the geometric distribution describes a situation where we have many Bernoulli trials, many trials that are either success or failure, and we're asking the question, how many times do I have to conduct this trial until a success occurs? So in the coin flipping example, if you're flipping a coin multiple times, and we're calculating the probability of the number of times you have to flip a coin until you get a head, we're to call that number of times x. That will follow a geometric distribution. So let's compute it here. So the probability of getting a heads on the first try is x is 1. That's when we flip our coin once and we get a head. So that's 0.5. And so now let's look at the probability of getting a heads on the second try. So really the wording is kind of confusing here. I should say having to flip a coin until a head occurs. And so if you have an older version of this lab, you're going to have to fix that. So the probability of getting a heads on the second try, flipping a coin twice and getting a heads, would be when x is 2. So we can calculate that by looking at the probability of tails first, right? And then probability of heads. So that's the probability of tails is 0.5, and we're looking at the probability of heads is also 0.5. So I'm going to copy this, see if we can reuse our work. What's the probability now of getting a head on the third try? Flipping a coin 3 times until a head occurs. So that would be our variable x being 3, meaning we have to flip tails twice, so I'm going to square that, and then get a heads. So if we flip tails twice, that would be 0.5 squared times 0.5. So you're starting to see a pattern. What's the probability of seeing 3 tails and then getting a head on the fourth try? That would be probability of tails cubed times heads, so it would be that. Okay, so if we want to generalize this to a formula, this is the formula for a geometric distribution. Probability of x equals n. If n is any number of times, we're looking at the probability of tails n minus 1 times the probability of heads. So we see a general formula that arrives out of this pattern, that we've developed. And so I'm going to plot this here. Okay. This is just a plot that's been made for you. There is one funny thing with the geometric distribution whereby it considers this argument n, the first argument here, and this means I'm doing 1 through 10. I'm actually just calculating the geometric distribution for 10 values. It has some offsets. It says that the value I put in, x, is the number of failures before success. So that offset is not very good. This means I have 1 failure before success, which we're talking about, we're getting success on the first one. So this is not something you really have to worry too much about, but if we want to get into the nitty-gritty, we're actually looking at 0 to 10 and 1 to 11 to make that correct, so that the first probability is 0.5 like we found. So this is now x like we thought it was. But we're not really going to use the geometric distribution because I think it's easier just to compute it by hand. And so this is the formula we just made. If p is the probability of success, well, we're looking at 1 minus p, n minus 1 times, and then on the nth trial we get a success. So let's not bother computing this in R. Let's just look at the insurance example that we've already done. And if we want to plot this same thing, the dgeom again has that stupid offset that I'm not going to bother with, so we can fix that. I had that incorrect the first time. But the only thing we change is the probability of success, which is 0.7. And so this gives you the distribution for meeting your deductible. And so then you can run that and have that geometric distribution for another situation. So the purpose of this is for you to see that the geometric distribution looks differently if you have a different probability of success. But what you guys really need to know is how to calculate it. So let's do an example with the meeting your deductible. The probability of meeting your deductible is 30%. So as we said, the probability of success is 0.7, not meeting your deductible. And so if we're looking at the probability of picking people at random and finding someone who doesn't meet their deductible until the fourth person, who met their deductible being the fourth person, that would be P of x equals 4. And so that calculation is 1 minus P to the 4 minus 1 is 3 times P. Okay, so if we want to have R do this, let's make an R chunk, put it in there, and I'll just call this P of underscore 4. And to see what that is, I have to display it. So that's our probability. That corresponds to this fourth bar here. So what's the probability of selecting people at random and not someone who meets their not finding someone who meets their deductible until the sixth person? So you see the pattern. It's the same situation where we can look at P of 6. And the formula is 1 minus P, where n is 6 now. So we got to put 5 here in the exponent times P. And so that's a nice way you can calculate. Okay, so this shows us the probability of selecting 6 people until you find someone who not finding someone who meets their deductible until the sixth person is really low. So that's useful information for an insurance company. Okay, so you guys got a problem you can work on your own. That's your assignment for this lab and for the rest of this section, and we'll continue with the binomial distribution in the next section. Good luck.